This is the analysis of the dynamic control system within a helicopter. To understand the analysis, we first need to see how a helicopter works. A helicopter swash plate allows the helicopter to change the pitch of some blades more than others, as shown in the video. This is what we'll be focusing on. Since we are only in 2D, we can simplify it to an up or down pitch. This brings us to our statement. Given a helicopter hovering, we'll be analyzing the stability of an aircraft with headwind effects. The image below shows the pressure of the wind acting against the surface area of the helicopters. The analysis will consist of an equation of motion, a block diagram, and general points on how the helicopter stabilizes itself. Looking more into it, we can see as the wind pushes the helicopter, its pitch decreases and increases. We follow the helicopter stability system to try and correct that it should be fully horizontal. We're assuming the helicopter should be 1,000 kilograms and to follow sea level conditions. There's only a wind velocity in the x direction.
As we analyze the helicopter, we break the forces into the fundamental x, y, and z axes. In the inertial body frame, there are a few main forces: the force of the wind, the force of gravity, the thrust from the main rotor, the thrust from the tail rotor, and the lift acting at the back of the helicopter, as well as torques that are results of spinning parts on the helicopter. In the first diagram, we look at the xz plane. Using F equals ma, we can look at the equations of motions of our helicopter. We can see that by adjusting the angle of attack, we are able to translate or rotate the helicopter. Our system needs to account for the force of the wind pushing on the helicopter to calculate the precise angle of attack needed to keep the helicopter stable. Also, changing the angle of attack has ramifications in the other planes. It is important to include these equations when it comes to maintaining stability.
This block diagram shows the control system we use to regulate the helicopter's motion. It starts with the reference values, things like pitch, angle, altitude, position, and velocity. These reference values are compared to the actual measured values, and the resulting error is sent into the PID controller. The PID converts this error into electrical signals that the actuators can use to adjust the helicopter's swash plate. The movement of the swash plate combined with any external effects such as headwind disturbances determines the helicopter's response, which is represented by the plant block. That response is then measured by the attitude sensor, and the sensor output is fed back into the system so the controller can correct this helicopter's behavior. The feedback path also includes some unavoidable sensor noise, which is added into the loop as well. Overall, the system shown in the block diagram is designed to keep the helicopter as close as possible to the desired flight conditions.
Just like most aircraft flight control systems, a PID controller will be used to address the attitude control of the helicopter in response to headwind effects. The KP term is the instantaneous tilt resistance, so it responds to immediate displacement in the helicopter's attitude as compared to the reference attitude and corrects them. KI is the integral term, which looks at the history of the error over a span period of time. It uses this to eliminate the steady-state error in the system, aka the errors that KP cannot eliminate, therefore allowing it to smoothly handle persistent, unchanging wind conditions. Finally, KD is the derivative term, which responds to the rate of change of error. This allows it to prevent overcorrection from sudden wind gusts and overshoot.